So continuing the topic, but before that let us revise a bit what all topics we had covered under the topic of electrolysis definition, then the factors affecting electrolysis, then Faraday's first law, Faraday's second law, electrolytic conductance, the difference between metallic conductors and electrolytic conductors, then the factor affecting conductance and resistance, solute, solvent, temperature and nature of electrolyte, then resistance, resistivity, conductance G, and conductivity kappa, then molar conductivity and molar conductance lambda m, that is given by kappa in 2000 upon C, that is molarity, and its unit is ohm inverse mole inverse centimeter square. Equivalent conductance, that is instead of molarity normality is used, and here the unit will be ohm inverse equivalent inverse centimeter square. Then we studied about the variation of conductivity and molar conductivity with concentration. So concentration decreases, conductivity decreases, okay, for both weak and strong electrolyte, but molar conductivity is inversely proportional to that of concentration. So if molar conductivity is increasing, therefore there is a decrease in concentration. If molar conductivity approaches, if the concentration approaches to zero, the molar conductivity will be known as limiting molar conductivity and will be represented by lambda naught. Coming next will be our strong electrolytes, which again lambda will be increasing slowly with dilution and will be represented by the equation lambda will be equals to lambda naught minus a under root of C. Okay, due to dilution what happens is the concentration of ion in an electrolyte gets decreased, so therefore the molar conductivity will get increased. Okay, and in the equation lambda is the molar conductivity and lambda naught is the limiting molar conductivity, whereas A is a constant that depends on the type of electrolyte and C is the concentration of ions. And the graph, if plotted between lambda, that is molar conductivity, and under root of C, that is concentration, a steep negative slope curve will be seen. Okay, coming to weak electrolytes like acetic acids and all, those have low degree of dissociation at higher concentration, so with dilution in these also the lambda will be increasing. Okay, and but an important case will be that at infinite dilution where the concentration will be approaching to zero, right? If we keep on adding water or something to an electrolyte, the concentration of ions will be approaching to zero, so the electrolyte will be dissociating completely. Therefore alpha, that is dissociation constant, will be equals to 1. Okay, so at such low concentration conductivity of a solution is low, therefore it cannot be measured accurately. So therefore weak electrolyte की अगर हमें conductivity we have to calculate, so there is a law named Coleridge law, okay, that we will be studying in this particular video. But continuing, so if we place the molar conductivity at y-axis and under root of C, that is concentration, at x-axis for weak electrolyte, the graph will be a rectangular hyperbola. Okay, so here the dilution's effect are very obviously clear, right? That on dilution weak electrolyte and strong electrolytes lambda will increase, right? Then in infinite dilution limiting molar conductivity will be increase, right? So when the concentration will be approaching to zero, limiting molar conductivity will be increased. Okay, Coleridge law will be used for weak electrolyte because to calculate the conductivity of weak electrolyte, because at infinite dilution electrolyte dissociate completely, and at such low concentration and conductivity the conductivity measure cannot be too accurately, right? So again that lambda m, that is molar conductivity with dilution, is only due to the decrease in interionic interaction. Okay, so when dilution will be done, the interionic attractions will be decreased, so therefore lambda m will increase. Simple. The reason for inversely proportional relation. So effect of temperature or conductivity will be directly proportional, right? Conductance ratio is the ratio of equivalent conductance at any concentration to that of the infinite dilution is called conductance ratio, that is shown by alpha. Okay, so alpha will be equals to lambda c, that is the conductance at concentration, at any concentration, and divided by lambda naught, that is the concentration at the infinite dilution. Okay, so Debye-Huckel-Onsager equation. What is this equation? This equation is the exactly same that we studied for strong electrolyte, but the only difference is that here A is being detailed. Okay, so lambda c, that is the conductivity, the molar conductivity at any concentration will be equals to lambda naught, that is the limiting molar conductivity, minus here a constant, okay, that is Debye-Huckel-Onsager constant multiplied by under root of c. So now what is this Debye-Huckel-Onsager constant? This is 82.4 divided by dt raised to the power 1 by 2 plus 8.2 into 10 raised to the power 5 divided by dt raised to the power 3 by 2 multiplied by molar limiting molar conductivity. Okay, where d will be the dielectric constant, t will be the temperature in Kelvin scale. Okay, so here this particular constant can be named as b. Okay, so in the shortest form it will be lambda c is equals to lambda naught minus b under root of c. Okay, so this b, the constant, is something that you should keep in mind, that's all. And it is very rare that we are asked to calculate b, but we should keep in mind this particular elaboration. Okay, for b is the constant and it depends on nature of solvent and temperature only. Okay, so in the next audio and video we will be taking Colruy's law. Till then, bye bye.